Okay, let's get back to A sub CFG. Any questions so far? So the cool thing that we determined was that any string of length n can be derived in exactly 2n minus 1 rule applications, except, of course, for the empty string, but we'll handle that soon. So here's what we're going to do. We're going to make a decider for A sub g, which is on input w, which is w1 through wn. So let's just handle that weird case where w happens to be the empty string right away, and then we'll handle the 2n minus 1 business. So if w is in fact empty, oh, sorry, it's not just w. It's the pair GW, the grammar in the string where w equals w1 through wn. We got to have the grammar there so that we can know. If w is in fact empty, then what should I check about the grammar? S goes to empty. Is G in CNF when I get it?
We don't.
Might not be. Do we have a procedure to convert any CFG into CNF?
Sure do.
Ah, we figured it out. I sense the sarcasm already. Oh, so let's put a step before to say convert G into CNF. Now we can check. Because the original grammar might not have that explicit rule, but still could make empty somehow. Well, if W is empty, well, what if S goes to empty is not a rule in the grammar? Could this grammar now make it? No, because the only way it could make it is if S goes to empty. So if W is empty, if S to empty is a rule, except if this thing is not a rule, reject. Because that's the only possible way that the empty string can ever be derived. And so now we just need to handle the 2n minus 1 business. Well, it says that every string of length n can be derived in 2n minus 1 steps. Do I know which one? I don't know which one, but one of them must probably works. If one works, then that's good. But what if none of them work? Can this string be derived? No. But do I know which one to do? I don't know which 2n minus 1 rules to look at. So what do? Look at every single possible way to have 2n minus 1 rules applied. So look at every sequence of rule applications of length 2n minus 1. Well, if the grammar could make W, then one of these is going to work eventually. So if one of them results in W, exactly W, and no anything else, no terminals, other terminals, no variables, nothing, just precisely W, then we should accept. Because we just found a way that the grammar can actually make W. Yeah?
Couldn't it take more than 2n minus 1?
No, because we found a way to derive W when we have CNF. And we can't have more than this because that would force us to make another variable, right? Because if I have, so do you agree right here that we have a precisely 2n minus 1? So if I had another rule application, one of them couldn't be one variable makes a terminal, right? Because I converted everything to terminals. So the only thing I could do is have one variable make two variables. But then that new variable has to make something of the string. But then I already just generated the entire string, but I can't generate empty for that variable. So in fact, it's exactly 2n minus 1. So I forgot the upper bound, thanks. Does that make sense? All right, so if one of them says is a way to make W, then we just found that the grammar can make W, so therefore we're good. Otherwise, that means none of them worked, which means that since it wasn't ever made, we must have it be that the grammar could not generate W, so therefore we reject. Because remember, we're trying to solve the A sub CFG problem. Okay, does that make sense? Yeah.
So rule applications of 2n minus 1, let's just say like 2n minus 1 steps.
Yeah, 2n minus 1 steps in applying rules, yeah. Yeah, any possible way to get 2n minus 1 steps, apply all of them. Any other questions on this?
And that's the, sorry,
Yeah, go
that's
ahead.
the decider for AC.
Yeah, so we should check. Does this first step take a finite amount of time? Yeah, because we found an algorithm that always halts for converting a grammar. It may take a long time, but we have a way to do it. Clearly, this first step, actually, no, it's not clearly. The second step, why does it take a finite amount of time? Right, and the grammar's length is finite. And so looking over all the rules takes a finite amount of time. Easy. This third step, does it take a finite amount of time? Well, n is a finite number, and the number of ways to apply rules, therefore it's some number, 2n minus 1 of them. That's a large finite number, but still a finite number. So therefore, it takes a finite amount of time, and of course the last step takes finite time. So it is in fact a decider, which is kind of cool. Any other questions though? Yeah.
Is the sequence of rule applications longer than 2n minus 1?
Of course, yeah. I can have an infinite sequence of rule applications. Like for example, this one. Not to generate a given string, no. Because every variable other than the start variable must make something of the string. And so if I keep applying rules, I'm going to be adding more variables, which means they must make something of the string, which is finite in length.
Yeah, so wouldn't it be then converted to Chomsky normal form that sequence of rule applications, all of them would be 2n?
It's precisely 2n minus 1, if it's not the empty string. Other questions? Okay, so how much time we got? Should I start? Yeah, I'll start it. So I'll just post this as a Piazza question, which is, it's actually kind of a cool result. What about E sub CFG? I give you a single grammar and I want to know, does it generate anything at all? So I want you to think about, and then we can have some discussion about whether this is decidable or not. Because we saw that E sub LBA and E sub TM are both undecidable, but E sub DFA is in fact decidable. So this is kind of like in the middle, so it can go either way, like A sub CFG could. Okay, so let's move on to the other thing. But other questions before we move on? Okay, so we talked about, for regular languages, this machine model for the regular languages, DFAs and NFAs. Then we talked about this regex thing for describing languages, and then we had this grammar for being able to generate languages. And then we generalized regular grammars to CFGs. But what are we missing from the context-free languages? We're missing a machine model for it. So what we're going to think about is another restriction of Turing machines. So remember, we had Turing machines, and then we restricted them to say, yeah, you can't use more than the input that you're given, which was LBAs. Then we said, okay, so some problems are undecidable there. Then we restricted it further to say, you can only move right, and so therefore you don't really need this tape thing. And then we got DFAs and NFAs out of that. So clearly, like languages like 0 to the n, 1 to the n, we need some more power out of this. And so what we're going to do is we're going to have this type of model. So let's say the input is here. And it's going to be the same thing as with NFAs. So we can only move right or stop. So the stop here means epsilon transition. So basically it just means it doesn't progress in the input anymore. But in addition to this, we're going to include a work tape. So this is called a work tape. So you can think of it like a multi-tape model of some kind. But we're not going to actually think of it that way. And if I just try to simulate anything on this work tape, then in fact I may get something that's more than the context-free languages. So we don't want that. What we're going to do is we're going to restrict what you can see on the work tape to just be the last character that's written on the work tape. So let's say that this is character C and then character D. I'm going to only see that D character and no other character. And if I want to say I want to move back in this work tape to see that C now, I have to take D away. I need to remove it from this structure. And then doing so will move the tape head of sorts back to C. And then if I want to put something else into this data structure, then I'm going to put it to the, let's say I put an E into this data structure. I'm going to put it there, and I'm going to move the head right to where that thing is. So what is this data structure? Where I can only see the end and I take things away on that one end or add on that end? Stack. So in fact, this is, instead of a work tape, we can think of it as a stack. Okay? So this is the model that we're going to think about. And the idea is actually very, very similar to the idea for problem set 5, the automata stack automaton thing. So it's almost exactly the same type of model. But instead of there, we're not manipulating the stack directly. We're going to manipulate the stack directly in this setting. Okay? And so if you look way back in the literature on this stuff, when they were first introduced, they were called these things called push-down stores. But we're talking about a finite automata model, so in fact they're called push-down automata. So instead of push-down store, push-down automata. So a push-down automaton. So this is a PDA. So it's not a public display of affection, but it's a push-down automaton. Well, let's see. It's going to behave exactly the same as an NFA, but it's going to allow you to put whatever you like into this stack. So, so it could be completely separate from the input alphabet. You can put whatever you like into the stack. Or, and you can have multitudes of transitions. You can push things into the stack, you can pop things off the stack, you can do both at the same time, and you can do neither if you like at the same time. Do I need anything else other than push or pop or neither or one of those? Do I need like a peek operation to like see what's on top of the stack?
You can just push and pop the same character.
Right, so but the thing is, I'm not going to see what's right on top of the stack there for a peek. To peek at the top element, if I push something on, then pop that off, then I'm not going to see this element.
You push pop the same thing.
But I need to pop. I see the thing when I pop the thing.
Okay.
So in order to see the thing, I need to pop it. And then when I pop it, then if I push it back on, then the contents don't change, but I know what was on top of the stack. Okay? So all the things of DFAs and NFAs almost apply here, except now we have what is called stack alphabet, and of course the transition function is going to change. So is a 6 tuple. So the 6 just means the 5 from DFAs and NFAs, but now we add the stack alphabet. So Q, sigma, as you might expect, but now gamma for the stack alphabet. So it's analogous to tape alphabet for Turing machines. So delta Q0F, where Q sigma Q0F are the same as an NFA, exactly the same. And gamma is the stack alphabet. And then we need to talk about the transition function in a second. Okay, well, let's see. This is like an NFA, so we have states and we read stuff and then we go to other transitions. But now we gotta account for this pop and push business. So we gotta fix here right now which one is going to indicate the pop and which one's going to indicate the push, or not doing either one of them. So of course I need to figure out which one am I going to do first. So should I do a pop first or should I do a push first? I should do a pop. Why? First. Because if I wanted to do a push and a pop, if I push something on the stack, I want to pop this thing, but now it's not on top of the stack anymore. So in fact, we need to allow you to pop first and then push. So that's what we're going to do here. So delta is going to be the same as an NFA, but now we have states cross either we can read something or not. So it's just a full generalization of an NFA. But now we need to say pop something or not pop something. So how do we say that? Pop something from what alphabet? Gamma. Or not. How do I indicate not? Union this set containing empty, just like with the input alphabet. Either you read something or not, you pop something or you don't. So it's exactly analogous here. But for what comes out of the transition function, since we're trying to generalize an NFA, let's just go full generalization and say you can go to any subset of what appears on the right side. But what appears on the right side is you go to a state and you either push something or you don't push anything. But since we want to apply any one of those possibilities, we need to do the power set just like as an NFA. So it's exactly the same as an NFA, but now we just stick a pop before and a push after the transition. So this one indicates pop or not, and this second one indicates push or not. Yeah.
Why don't we multiply that to the delta transition?
I'm not sure what you mean.
Why don't we multiply the power set so we have the option? Can we pop and push in the same transition function? Or?
No, it's the same thing. It's just I tell you what you can pop, which means if this thing is on the stack, now you can apply a transition. You could apply this transition, and then you can push. You can have many transitions that could push something or something different. So it's telling you if you happen to be in this state and you happen to see this character and you happen to look on the stack and see this thing, then here are the multitude of transitions you could apply. So it's just, if you just ignore the push and pop, it's the same thing as an NFA. But now I have, if I see an X on top of the stack, then I could apply these 7 transitions which correspond to popping an X, but maybe pushing something or something else. And we'll get to an example. But any other questions about the definition? Yeah.
I think it's a follow-on from the last question. That the pop and the push in this format seem like they're getting lost. I don't see where they're actually.
So note, does the pop occur before the transition occurs or after? Before the arrow or after the arrow?
Before the arrow.
Before. So the key here is ignore the pop for a second and just focus on this. That's like an NFA, right? So think of an NFA. You're in a state and you see you're in some state and you see a symbol on many transitions. You can apply any of them, right? So remember, that's the power set of Q. You can go to any set of states. But here we're going to say, I'm just going to do it informally. So let's say we pop X here and maybe pop Y on this one and pop Z. Before, for the NFA, I could apply any one of those 3. But if X is on top of the stack, how many can I apply here? I can only apply 1 because there's only one transition that says pop X. If there's an X on top of the stack and I see a transition that says pop Y, could I apply that transition? No.
Okay, so the pop operation is not popping a character, it's popping a specific character.
Right, a specific character, yeah. Yeah, so the way that we know what's in the stack is via pop. So if I say I'm gonna pop an X, I can only apply that transition if there's an X there. So we'll see, the example will definitely help. Yeah.
So does that mean the stack can grow more than 2 characters?
Why not?
Like, you either have a character in this pop, we have epsilon, but doesn't epsilon mean that there's nothing pop?
Well, the example will help, but the idea is you can have a whole bunch of transitions at the beginning that just don't pop anything and push on a whole bunch of stuff, and then a whole bunch of transitions on the end that pop all of them but don't push anything. Yeah.
That's why we can do push pop, because we have, when we're popping, we specify what character
Right.
we are looking for.
Yeah, we specify what character to pop, and then that'll give us a whole bunch of transitions that correspond to going to some state and pushing something. Yeah.
I didn't fully hear the question, so I think it might be pretty much the same. It's just
Can you repeat?
I said, the reason why we can't push and then pop is because when we apply the pop procedure, we have to specify what character we're going to pop.
Yeah, so the way that a transition can be applied is looking at the state you're in, what character or not that is on the input, and what character you want to pop or not. If you fit each one of those 3 categories, then you could apply that transition if you'd like. But of course, there can be many transitions. But other questions? Okay, so first off, what are the languages of PDAs relative to the regular languages? Well, what if I just have one of these PDA things that just doesn't push or pop anything, just does nothing with the stack? Do I need the stack at that point? No, so what is that thing at the end? It's an NFA. So if I don't use the stack at all, I just get the regular languages out of it. So if I want something for a non-regular language, I better use the stack in some way. So let's make a PDA for our favorite language, 0 to the n, 1 to the n. So basically, I hope to see a bunch of zeros and then a same number of ones on the end. And we know this is not regular. because we proved it. But how could I use a PDA to help us here? Well, I can try to keep track of the number of zeros, but how do I keep track of that number? Oh, why don't I just put them on the stack while I'm reading the zeros? But then at some point I'm going to see ones. So if I see a 1, what should I do? I pop a 0 in tandem. So I see a 1, and at the very same time I pop a 0. At the end, what should I see at the very end? If I've read the whole input, I better see an empty stack. Do I have an empty stack operation? Could I simulate having an empty stack? What's the way I can simulate having an empty stack without actually having one? Add a special character. And then at the very end, what am I going to do? Pop that character. So if I see a 0 on the stack after seeing the whole input and there's still a 0 on the stack, should I accept? No, because it's not the same number of zeros and ones. Okay? So that's what we're going to do. So we're going to have a state Q0. And the very first transition is going to put on this special character. And the prototypical one for these is a $. So the way to indicate a transition here is, now I forget. Yeah, so I'm trying to remember where the arrow goes. Okay, so am I going to read anything while pushing on this special character? No, I better not read anything because the reading transitions correspond to pushing on the zeros and then popping off the zeros. But I'm not doing either one of those things here. So I better not read anything. Should I pop anything? Because the pop has to happen first. No, because what does the stack start out as? Empty. And if I attempt a pop on an empty stack, what happens? The world explodes. So we need to not have the world explode. We need to say, yeah, we're not going to pop here either. But are we going to push something? Yeah, so we're going to push on a $. You can put on whatever character you want because remember, the stack alphabet has nothing in relation with the input alphabet. But in this case, it happens to include $, and 0. Yeah.
What's the arrow?
So the arrow just indicates, I'll just write it in English. So the first thing in here is read, the second one is pop, the third one is push. So it's in the same order as the transition function definition. So here I'm saying I'm reading nothing, I'm not popping anything, and I'm pushing a $, onto the stack.
So why do we need the arrow?
It's just the convention for the transition, the way the transition's written. Yeah.
Read epsilon means you go right on the
Right, I'm not reading any characters, just like an NFA. It's exactly the same as an NFA, but now I have these push and pop things. Other questions? Yeah.
So even though we're using a DFA with stack, we could look at a tape sort of because we weren't used to thinking about tape with DFA, right?
Yeah, you could think of it that way, but so the whole reason for each of these models is a restriction on Turing machines. So it was a motivation to think about some restriction in between DFAs and full-blown TMs, but I would think of it in terms of a stack, not as tapes, because it'd be easier. But it is, the motivation is as a restriction. Other questions? Okay, so here we go to some state Q1. So we put on this special character $, and then now what is our task? So what was the idea?
Push on zero.
Right, push on the zeros. And so what am I reading as we go? Well, we better see zeros. Should I see a 1? No, I hope not, right? So, but do I know how many zeros am I going to read? I have no idea. So I'm going to do a self loop in this state because I have no idea how many I'm going to see. So I'm going to do a self loop and say, yeah, I'm going to in fact see a 0 here. Am I going to pop any of these times? No, because my job is to put on the zeros. So I better not pop anything, but should I push something? A 0. You in fact don't have to put on a 0, but you need to put on some character and deal with the same character later. But it's usually good to have the same thing here to make it easy to work with. Well, do I know when the 1s are going to come? No. Well, in fact, I could read a 1, but what if I had a transition that just had a 1 and some other stuff? Would I have the same language as the one up here? No, and what string would I miss? Our favorite string. Empty string. Because if I want to come down this transition, I need to read something. But the language says the empty string is in there. So I need to have the empty string in there somewhere. Luckily, PDAs are non-deterministic. So in fact, we can have epsilon transitions like that first one, where we can just instantaneously, if we want to, go to another state. So here, we're not reading anything, and for that reason, we're not popping anything, and we're not pushing anything either. So this is my term, I call it a triple epsilon transition. So a lot of epsilons, obviously, but the whole goal of here is to say, I'm finally done seeing zeros. I'm non-deterministically guessing to now start reading the 1s. And this will help us get the empty string, which is in the language anyway. So we need to be able to handle this string no matter what. But setting that aside, what was our next goal after pushing on all the zeros? What do we hope to see? A 1. And if we see a 1, what should we do with the stack? To just pop up all the zeros at the same time. So, and I don't know how many I'm going to see, so I better hope to see a 1. Should I pop anything? Yes, a 0. The same character as the one we pushed earlier. Should I push anything? No. So I'm not going to push anything. And at the end, when the dust settles, the fight's over, what do I hope to see on the stack? $sign. And how do I know when the $sign is on the stack? I need to be able to pop the $sign off because that's the only way I know that $sign's there. I could re-push it on in the same transition if I wanted to, but do I have to end with the stack empty? I, in fact, do not have to end with the stack empty. I could, and in fact, in this case we will, but I don't have to have the stack empty. So here, I better not read anything because I better have done all the reading already. I better pop off the $sign, and I could push something, but in this case I won't. So, and at that point we accept because the only way we can apply that transition in the first place is if the 0s and 1s matched, which means that the original input was accepted by the PDA. Yeah?
So if you have 2 epsilons on the left, does that work just like an epsilon in a normal NFA, or it automatically follows?
Yeah, so the triple epsilon is akin to a NFA, just a normal epsilon transition. But here, I could, for example, in that transition, push something if I wanted to, but I better not in this case because I would change the language. But there's nothing prohibiting me from putting something.
And it will still auto go like normal epsilon?
Oh, no.
Like,
Yes, in this case, because what determines when you can apply transition is the first 2.
Okay.
Well, in addition to the state. So,
so if you could convert this to a DFA, and you can't, but
yeah.
Would the first initial state be Q0, Q1, and
Q3. Because there's an epsilon transition there.
But it needs to be on the stack.
Yes.
So,
yeah. So the stack really does change things here.
Interesting.
So like for this transition, the only way I can apply that transition at all is if a 1's on the input and a 0 is on the stack. If either one of those is not true, I cannot apply that transition at all. But if both of them are true, I always can apply that transition if I want to. So same thing with the last transition. If there's, I don't have to read anything, so I automatically satisfy the reading requirement, but I have to see a $ on the stack in order to apply that transition. For the first transition, I automatically am able to apply that transition because I don't have to read and I don't have to pop anything. So I always can apply that transition. Yeah.
Couldn't there be a weird situation where you put on like 3 zeros and you were going to take off 4 1s, but since it didn't see...
Great question. So what about that? So I'll do a simpler input. What if I had more 1s than 0s? So let's trace through. I go to Q1, I put on $. I put on 2 zeros, then I instantaneously go down to Q2, then I pop those 2 zeros, and then now what's on the stack? $. Can I apply the Q2 transition? No, because it doesn't satisfy the popping requirement. It satisfies the reading requirement, yes, because there's a 1 still left in the input, but the 0 is not on the stack anymore, so that won't work. Okay? What if I had the opposite problem? I had more 0s than 1s, because you got to think these things through. Well, I put on 4 zeros as usual, go down to Q2, pop off 3 of them, and I can go over. But, sorry, I'm in Q2 and I pop off 3 zeros. Can I apply that last transition?
You can't pop a $.
Can't pop a $ because the 0's on the stack. So I can't enter the final state. But think back to your example for a second, because it's actually pretty interesting. If I have 2 zeros and 3 1s, if we go down to Q2 and I pop off those 2 zeros, right? So there's a 1 still in the input, okay? But there is a $ on the stack. Can I apply that transition that goes to Q3? Yeah, because it says, I already satisfied the reading thing, and there is a $ on the stack. I can apply going there, and I went to a final state, so therefore I accept this input. Is that true? No, why is it not true? I haven't finished reading the input. Just like an NFA, I need to read the whole input in order to accept. So I have to read the whole input and be in the final state. So in this case, I am in a final state, but I don't read all of the input, so therefore I can't accept. But if I removed one of those 1s, then I have read all the input and I'm in a final state, so I accept. Does that make sense? Yeah.
So if you're in the final state and you have input left, those unmarked transitions would kind of like go to rejection states.
Right. So there's no rejection state like an NFA. So like there's no transition coming out of this state on 1 or whatever. In that case, well, there is an epsilon transition, so I could go down if I wanted to. But supposing that that's not the case, if there's no transition to apply, then the machine just stops, just like an NFA. Yeah.
I wanted to clarify what you said previously. So you would end up in Q3, but you haven't finished reading?
Correct. In his example where we had 3 1s. Yeah, because the first 2 zeros are handled in the Q1 self loop, and then in the Q2 self loop, I handle 2 of the 1s by popping them off. I can't apply that a third time, right? Because there's no 0 on the stack. But I go over to Q3, I'm in the final state, but I haven't finished reading the input. So therefore, I can't accept because I didn't finish reading.
Okay, is there a notation for that?
For what?
For not being in the final state, but not being in accepting?
No, it just, this string is not in the language of the PDA. So so if I have a differing number of 0s and 1s, this PDA cannot possibly accept because even if I'm in a final state, we just showed that you can't go to the final state and have read all the input, which means that string cannot possibly be accepted by the PDA. And it doesn't handle zeros and ones in any order because the way that it's set up is the only pushing happens when I read a 0 first, then the only reading of 1 happens when I pop a 0, and if I want to pop a 0, that must have been preceded by a 0 push. And so therefore, it must be same number of zeros and ones with the zeros before the ones. So therefore, it's 0 to the n, 1 to the n. Yeah.
So is this a PDA for that language or not?
Yes, it is. So I'm just arguing why it's correct.
Okay, I guess I'm just confused that you can wind up in Q3 but not actually.
So think of this. Go back to NFA land. So think of this. Think of the input 1, 1 for this NFA. Is this NFA accepting? Does it accept 1, 1?
Yes.
How?
It takes the one transition and can't go anywhere else and then finishes reading and then it accepts.
No, look back at the definition of computation. It says that if we can break this string up into pieces, the entire string up into pieces, and we read the entire thing and land in a final state. The formal definition of computation takes the entire string. So it can't. So in fact, there's no computation at all. It's not even an accepting one. There's no computation at all of this string because there's no way to read all of the input. Whereas, for example, if we augment this with epsilon here, and I just look at just the empty string, how many computations are there of this NFA on that string? At least one. What if I take that self loop twice? So in fact, there are infinitely many computations of that string. But are there any accepting computations? No, because there's no way for any of those computations to end in a final state. If, for example, I make that start state final, then how many accepting computations are there? Infinitely many, yeah, because I can take that as many times as I like. So we didn't define computation formally here, but it's very identical to NFAs in that you have to read the whole input because we need to break it up into each of the transitions. So remember back at the definition of computation where we say where each character in the input is either a character or empty. So we stick in empty strings wherever we like, and each one of them corresponds to a transition of the NFA. So here it's almost the same, but we need to take account of the stack as well. So I would advise looking at the formal definition because it takes the entire string. Yeah.
If we were to make a transition from Q3 to like Q0 on like a 1, would
Yeah.
that be wrong, or?
It would be a different language, yes.
Why is that?
Because well, it depends on what you push and pop. So, well, I better not pop anything at Q3. Why?
Because it's empty.
Yeah, because it's empty. And if I pop anything, I can't apply it anyway. So let's say empty, and I don't push anything either. So the language here then would be 0 to the n, 1 to the... So this is not quite precise, but star... no. N plus 1 star, where you take a different number of zeros and ones possibly every time. Okay?
Wouldn't you end up in a non-final state? Or you can loop back around?
Right, you can...
Okay.
Actually, this is not quite right either. Yeah, it's not quite right. The point is it changes the language. Yeah. And we wanted 0 to the n, 1 to the n. So in fact, we just showed that since every regular language can be recognized by a PDA, and we just showed a PDA for a non-regular language, this model does in fact have more languages than the regular ones. Okay? Cool. 11 minutes. Plenty of time. All right. Yeah.
Instead of just people epsilon transitions, why don't you make 1, 0 and epsilon 1?
Great question. Why don't I do this on that middle transition? What string would I miss? The empty string, right? Because there's no way for the empty string to go to the only final state, right? Because the only way to get there is actually reading at least one character from Q1 to Q2. So that means I must have read some character. So therefore, it cannot possibly accept the empty string.
How does the empty string get from Q2 to Q3?
But I need to go from Q0 all the way to Q3 because Q3 is the only final state.
Right, I'm asking how would the empty string get from Q2 to Q3?
Q2 or Q0?
From Q2 to Q3.
It could, from Q2, but how do I get to Q2 from the start state?
Well, the way we first described.
Right, but I changed it to say this on the transition. So I have to read something going on that transition.
So in our original configuration,
Right, yeah.
how do we get from Q2 to Q3 with the empty string?
Yeah, of course, yeah. So that's why it was triple epsilon, because we need to have the empty string in there.
Can you make 0 and 1 parallel state?
Yes, I could. So, yes. So you're right. I could do this instead by making Q0 final. That would be another way to do it. But I'm just showing a prototypical way to bake this PDA. Yeah, because now the empty string is accepted just by staying in Q0 and immediately accepting, because I've read the whole input and we're there. Okay, any other questions? Okay, let's see. And so what we want to show then by trying to introduce this model is, do they in fact recognize the context-free languages, or are they in fact something different? And what we'll show is that they in fact are the right model for context-free languages. So we're going to do the easy direction today and then the hard direction Friday. So what we're going to show is every CFG can be converted, or at least we'll do it partially today, into a PDA. An equivalent PDA. So it has the same language. So this would show that every context-free language can be recognized by a PDA. Well, let's see. How in the world are we going to show that? Because we got to convert this thing that has variables, terminals, rules, and all this stuff into something that has states and a stack and reading and who knows what else, right? It seems rather different. So here's the idea. Can I apply it for a grammar? Can I apply any rule? If I'm looking at a variable s so far, can I apply any rule corresponding to s? Yeah, because it's a context-free grammar, right? So if an s appears in the derivation so far, I can replace s with anything that has s on the left-hand side, any rule that corresponds to s, right? So CFGs are non-deterministic that way. Are PDAs non-deterministic? Yeah, because we define them as a generalization of NFAs. Well, let's see. What is this whole class about? It's about, well, a lot of things, but it's about doing these simulations of one thing or another. Think about the regex, about the NFA to regex process. So we have these regexes on the transitions for the generalized NFA, and we were trying to simulate the original transitions. What if I could simulate the derivation of the grammar on the stack? Okay? What if I could do that? Suppose we could. Would this be enough? Yeah, so if we can simulate the derivation on the stack and there's nothing left on the stack at the end, meaning we've matched it up with the input, is that enough to show that every CFG can be converted to a PDA? So, in fact, that's the case. So let's look back as an example, so because I won't have time to do it. But let's look at our example for 0 to the n, 1 to the n, for the grammar. And let's say we try to make a PDA for this. Well, what does every derivation start with? If I want to start applying rules, I'm going to need to start somewhere. Start variable. Is that enough enunciation? But the start variable is the start of the derivation. So if I want to simulate the derivation on the stack of the PDA, I need to put the start variable there, right? Well, let's say we're trying to do this derivation and we're matching up with the input of the PDA. So remember, PDAs have inputs, CFGs do not. So if I'm doing the simulation of the PDA of the grammar on the stack, and I'm matching it up with the input, and everything works out, I've matched it up with the input, and there's nothing on the stack left to actually work with. There's no variables on the stack, there's no terminals on the stack. What is the stack now? If I've popped everything off the stack is empty. Well, how do I say, now I want to accept? Well, I need to be able to go to an accept state, right? But I need to check whether the stack is empty in order to say, yeah, I accept. Because even if I've read all the input, the stack might not be empty. And therefore, I might not have had a derivation of the string that I want. So I need a way of saying, okay, now the stack is empty when I take this transition. So what was our trick for that? Put some special character on. So that's exactly what we're going to do. So here's the high-level idea, and I'll let you go. So push on $, and then we're going to push on the start variable. So the stack contents now are $, on the bottom and the start variable on the top. Okay? Well, what's going to happen? What's going to happen is I'm going to repeatedly do step 3, which is, so if a terminal on top, we're going to match with the input. So if a 0 is on top of the stack and I see a 0 on the input, I'm going to read it off the input and I'm going to pop it off the stack at the same time. Because remember, when a terminal is generated with the grammar, is it going to ever change? No, because it's not a variable, and in fact it's a CFG. What if a variable's on top of the stack? What do you think we should do? We're going to apply one of the rules of the grammar on the stack. We're going to simulate the derivation. And if another terminal pops up, we're going to match it up with the input. If another variable appears, we're going to apply another rule. So we're going to simulate the derivation of the grammar on the stack. So if variable on top, apply a rule and put it on stack. There's a subtle detail here which I'll leave till Friday. I'll let you think about how do you actually put the rule on the stack. But hopefully at the very end, we're going to have a transition that says if the $'s on top of the stack, meaning the stack is empty, then we accept. So if $' on top have transition to a final state. So that's actually the entire idea at a high level. We're just simulating the derivation of the grammar on the stack. Okay? Any questions before I let you go? Cool. I'll see you on Friday.